All right, this is our last section in Unit 2B, and we're going to be talking about the factors that affect the rate of a reaction, how fast or how slow a reaction will occur. Kinetics is the term we use to describe how fast a reaction occurs, and we can measure quantitatively the reaction rate, which is just the change in the amount of reactant or product in the chemical reaction per change in time, as seen in the green box. Now there's a very important theory called the collision theory that basically says in order for molecules to react, they have to have effective collisions. And there are three criteria that must be met for an effective collision to occur. Reactants obviously have to collide with one another, but they also must collide at the correct orientation, angle, and they must meet a minimum energy for the reaction to occur, which is called activation energy. So how does this relate to reaction rates? Well, there must be an increase in effective collisions in order for the rate of a reaction to speed up, or a decrease in effective collisions for the rate of a reaction to slow down. One of the most important things to understand is that millions and millions of collisions are happening in a reaction, but only a small number of collisions will actually meet the requirements and result in a reaction. Remember, all three of the following criteria have to happen. You have to have a collision, it has to be at the correct orientation, and it has to have the right activation energy. This visual helps us understand the criteria for an effective collision. Remember that molecules must hit each other with the right amount of energy, which is called activation energy, and they must be in the correct orientation. If we take a look at the top diagram, you can see that the reactants are not moving very fast. They don't have enough activation energy, so the molecules bounce off of each other and there is no reaction. In the second portion of this diagram, it tells you that the reactants aren't facing in the correct direction. And once again, we see those molecules bounce off of each other and no reaction. It's only when there's enough energy in the reaction to meet the activation energy and that the molecules are correctly oriented that a chemical reaction will actually occur. So this is a reaction coordinate diagram which shows us the energy changes through a chemical reaction. There's a couple of areas that you need to be able to identify. The reactants will always be on the far left, just like in a chemical equation. The products will be on the far right, as also in a chemical equation. And there will be a line that connects the reactants to the products in a curve. At the top of the curve, you are going to have the activated complex. It is also known as the transition state, and it is a temporary molecule that is formed as the reactants have twisted and vibrated and have almost broken apart in order to form the products. Remember that in a chemical equation, the reactants must break their bonds and reform the new bonds of the products. One of the most important things, especially in this section, is how you figure out the activation energy of a reaction. Activation energy is always the amount of energy that it takes for the reactants to get over the hill to reach the activated complex, the transition state. We abbreviate that as EA. One other thing that you need to be able to calculate is the change in the energy of the reaction, also known as enthalpy. And we will talk more about this when we get into thermo, but it is basically the difference in energy between the reactants and the products in the curve, and it's called delta H. The delta stands for change, H is enthalpy, which means energy, the change in energy of a reaction. And we will learn that when you have an uphill curve, like we see here, that you will have a positive value for delta H, and that will tell you that you are actually looking at an endothermic reaction. What that means is that those reactants must gain energy from the surroundings to get over the hill. So now we need to discuss the 5 factors that affect the rate of a reaction. The first one is called the nature of the reactant, and it basically is telling us that there are just some substances in this world because of their atomic structure that are more reactive than others. such as the alkali metals being more reactive than, say, the transition metals. The second factor is the surface area of reactants. How does the surface area affect reaction rate? Well, the more surface a reactant has, the more often the reactant surfaces can come in contact with each other, and then we're going to get a collision. And that's going to then increase our effective collisions. So as surface area increases, more effective collisions can occur, and reaction rate will increase. So if we take a look at this visual, it just reminds you that when a solid is reacting, it can only react on the surface of the solid. And you can see that as we move through the first, second to third diagram, as I pulverize a solid into smaller pieces, more surfaces become available. And that allows for an increased area of collision. And we just talked about how more collisions, there's a greater chance for a reaction. The third factor is concentration of reactants. So how does concentration affect reaction rates? Well, remember that concentration is how much of a reactant is in a certain amount of space. And the more concentrated we are, the more reactants will be within that space, the more crowded it will get, the more effective collisions will occur. So of course, if we increase the concentration, we increase the reaction rate. Now, down at the bottom, there is a way that we can describe the concentration of an aqueous solution. And hopefully you notice that the acid that they're talking about here is hydrochloric, and they're comparing the 1 molar hydrochloric acid to the 3 molar hydrochloric acid. Molar is really the moles of the substance per liter of solution. As this number right here gets larger, it gets more concentrated. So this is the more concentrated acid, meaning that there's more molecules of acid in 1 liter than there is in the 1 molar. And so because this is more concentrated, you would have a faster reaction if you added something to that hydrochloric acid. This slide is just reinforcing that at a higher concentration, you're going to be more crowded, molecules are going to collide with each other more often, and you will then get more effective collisions in that process. Temperature is the fourth factor that affects reaction rate, and it affects it in several ways. The first being that molecules at a higher temperature will have a higher average kinetic energy. Kinetic energy is energy of motion, which means that the molecules are going to move faster, and they're going to collide more often, giving us more effective collisions. But that's not the only way that temperature affects reaction rate. Since temperature is a measure of the average kinetic energy, and remember that molecules must collide with a minimum activation energy, we can actually use that kinetic energy and transfer it into the form of activation energy to get the reaction to occur. So at higher temperatures, there will be more molecules able to attain that activation energy because there's more energy in the surroundings. So they say a rise in temperature of just 10 degrees Celsius can actually double the rate of the reaction. So remember, for most reactions, as temperature increases, reaction rate will increase as well. Not only does it increase the collision frequency, like we've seen in the other factors, such as concentration and surface area, but it also increases the effectiveness of the collision. Because at a higher kinetic energy, more molecules will be able to attain that activation energy that they need. So if you see someone stuck on the side of the road on a cold winter morning, it could be their battery. If temperature affects reaction rate, at lower temperatures, the rates of the reactions are going to be slower. The kinetic energy is lower, the molecules are not moving as fast, and so the electric current that is going to be generated from the reaction in the battery will proceed more slowly, and that means that there will be less likely to deliver enough current to meet the demand on the car. The last and fifth factor that affects the rate of reaction is a catalyst. Catalysts are substances that will increase the rate of the reaction without being used up. If we take a look at the reaction in the middle of the page, you will see that there are 3 reactants, A, B, and C. And then the arrow, which means to yield, and then our 2 products of D and C. Notice that C is found on the reactant side and the product side. C is a catalyst. Okay, it is a substance that is not used up. It is present at the beginning as a reactant and then is then produced back out as a product. In your body, enzymes, biological enzymes, are catalysts that will speed up the bodily reactions that keep you moving and alive. What you need to know about the catalyst is that it's actually going to change the pathway of a reaction. And as it does that, it will lower the activation energy, which will create a faster reaction. Now, if you remember from the reaction pathway discussed a couple of slides earlier, the reactants will always be on the far left, the products will be on the far right. And if we take a look at the pathway that does not have a catalyst, if we were to look at the activation energy there, you would get an amount of about that much. And if I add a catalyst, you'll notice that the level of reactants stays the same, the level of energy stays the same, but our transition state is actually lower, and the level of the product's energy is also staying the same. So because we have a lower transition state, we're actually going to have a lower activation energy. A lower activation energy means faster reaction. So many catalysts are transition metals or compounds of transition metals. To give you a couple of examples, we've got nickel, which is the catalyst for the production of margarine. We've got iron, which is the catalyst for the production of the cleaning agent ammonia. And you've got platinum that is found in the catalytic converter of car exhausts. And it does something very important. As the car produces carbon monoxide and nitrogen oxide, which are very poisonous and harmful gases, the platinum will actually convert it to less polluting and more friendly gases of carbon dioxide and nitrogen. Catalysts are very important in industry. Not only are products going to be made more quickly, saving that company time and money, but the catalysts are also going to reduce the need for those super high temperatures, saving fuel and reducing pollution. I leave you with one last very important idea, and that is that catalysts are called enzymes in the human body, and they are extremely important in our living cells for the function of them to get those very important necessary reactions to happen every day. So thank your enzymes, and that's the end of this lesson.